Chapter 23 focuses on substitution reactions of carbonyl compounds at the alpha carbon. So alpha carbons, and we will discuss what alpha carbons are. So let's begin with the acidity of alpha hydrogens. Again, alpha carbons and hydrogens they go together. So the hydrogen atoms bound to the adjacent carbon or carbon adjacent to the carbonyl carbon of an aldehyde ketone or ester are acidic enough to be removed by a strong base. So where are those hydrogens? So they are on the adjacent carbon. So let's use, so here's our carbonyl carbon. Here's our alpha carbon. And this is, of course, going to be also the alpha hydrogen. So again, this is, I'm going to write this there. That's called the alpha carbon. The next one is called the beta carbon, and of course, a beta hydrogen. So it says once deprotonated, the carbanion generated is stabilized by delocalization of the negative charge to the oxygen atom of the carbonyl. So if we look at the pKa of the alpha hydrogen, the pKa is around 20. So that's for the alpha hydrogen. If we look at the pKa of the beta hydrogen, it's around, or it's between 40 to 50. So this is nowhere as acidic as that one. So this is acidic, and this one is not acidic. Acidic. Now, why? It's because we have, if we get a negative charge on that carbon, this negative charge on that carbon, we will show you that. Don't worry, we're going to show you this in the next, when we discuss the three reasons. This negative charge can be delocalized onto the carbonyl group here, of course, and the carbonyl oxygen. So just a few things about pKa. So if you remember, the pKa's of alcohols are around 15. So alcohols are more acidic than alpha carbons, alpha hydrogens. Aldehydes and ketones are around 20. Now esters are around 25, same as alkynes, around also 25. So you can see that alcohols are the most acidic, and at least in this comparison, and esters, alkynes are the least acidic. So let's take a look at the carbonyl effect on the acidity of the alpha hydrogen. So it says, the question here, what is the alpha hydrogen of a carbonyl compound? Why is it so much more acidic than the typical H bound to a carbon? So let's take a look. So if we have an R group here, and we have, and let's actually make this a carbon shown. So here's that H. So that's our alpha carbon and alpha hydrogen. So if we have a base that deprotonates this, we would get with the lone pairs shifted back to that alpha carbon. So there is, the first reason is the carbonyl is electron withdrawing. We've learned about this since the beginning of the semester, even with the Diels alder, how a carbonyl group is electron withdrawing. So what has happened here is you have an inductive effect. So you have an inductive effect because of that oxygen drawing electron density toward the oxygen. Remember, the oxygen is electronegative. So let me write that down here. The inductive effect of the carbonyl makes the negative charge more stable. So that's the first reason. Once again, this should be a review because we did discuss this before. Now, the second reason is, you guessed it, is resonance. Resonance is always playing a role when you have a carbonyl compound. So let's look at resonance. So once again, we have a base here, deprotonates the alpha hydrogen. And we're going to need brackets for the resonance here. So what's going to happen is you have the R group. We're going to put the electrons on oxygen, carbonyl oxygen, and then of course you have a CH2 with a lone pair. Now, so what's going to happen with resonance here is these electrons are going to shift in between, and then the pi bond in the carbonyl will break, shifting the electrons to oxygen. So here are resonance arrows. Remember that. Right there. So this is the minor. This is the major, simply because the negative charge is on the more electronegative atom. So the negative charge is on the more electronegative atom. So oxygen is more electronegative than carbon. Accommodates, let's misspell this, accommodates charge or negative charge better. So this is what we call, we have a name for this. We call this a resonance stabilized. This is the new term, enolate ion. This right here is called an enolate ion. An enolate ion. So this is the second reason. The third reason is, I kind of discussed it already, but here it is again, just to separate the negative from the, to emphasize the importance of having that oxygen versus, let's say, having an alkene here. And that is, if you have a base Once again, a base, and bases have a function, and that is to deprotonate. So they deprotonate a carbon. And in this case, of course, we said that this would be, the result would be a CH2 lone pair and a negative charge. Here you have, again, the same thing. Okay, there's a CH we forgot here. CH. And oh, we're going to put those electrons on there. Okay, so they both have resonance structures. So the question is, which one is the better resonance stabilized? So we'll put those. Right there. So again, why is the carbonyl with oxygen in it, why is that makes the enolate more stable? Once again, it has to do with the more electronegative oxygen. As I stated before, this is say here, the negative charge is delocalized onto more electronegative oxygen. So here you have a carbon and a carbon. Here you have a carbon, but an oxygen, and an oxygen with a negative charge is much more stable than a carbon with a negative charge. It's not as electronegative.